Hi everyone, this is Team 10, London Aquatic Center, 리준수, 고재성, 신선웅, 림영규, and Yang Jae-young. This week, we've studied about the internal system of the building. Because the building is for the Olympics, internal systems such as ventilation, cooling, and heating system should make necessary environment for the spectators and the athletes. This week's contents is review ventilation system, heating and cooling, and water system. Last week, we studied about the interior construction. We focused on the swimming pool, diving stand, and seats. From now on, we'll start a simple review of last week's content. To allow us to ensure that the reinforcement could be bent and placed, they developed geometric definition software that extracted the three-dimensional position of all bars at each section and generated the best fit single plane radius bar. London wanted to keep the structure and use it as a community center, which the city was lacking. Zaha Hadid and our architect's solution was to have 50,000 temporary seats that would attach to the roof, and it needs 170-ton steel truss, meaning there would be no need for columns or other supports that would block views. First, let's see the ventilation system. To understand its system, we must know the air movement strategies of the building. London Aquatic Centre employs a variety of ventilation techniques, including both natural and mechanical methods. They try to make the air move in a certain way. Air is supplied to the major event spaces using oversized ducts below the pool deck, providing the freshest air at the level of highest activity. In addition, the ventilation system employs only low-velocity jets and fans, avoiding drafts and helping to establish both a pleasant and consistent ambient environmental experience. To make a best condition for the athletes, they try to make fresh air condition, especially for the pool side. They call the pool side as Comfort Zone 1. This is how it works. First, air is released through vent in the seating wall, and the air is heated by the water-based radiant heating system in the floor. Next, the natural rise that follows allows fresh air to dominate the pool space, while cooler, older air falls and is caught in return duct. This whole system provides for a warm, well-ventilated environment for the athletes. The duct I just mentioned supplies both water and air in the pools. By combining a supply and return into duct, they made a huge duct for the center. This duct was oversized enough for human access, while also allowing for easy maintenance to the central filtration room. Also, there are comfort zone 2, spectator seating. As the building was for the sports game, seating environment for the spectators are important too. Due to the significantly cool atmosphere desired by spectators as opposed to the athletes, the seating was an entirely different system than the pool side. Each seat is supplied with its own under-seat vent, which supplies the desired cool air directly to the individual spectator. The air is cooled with a series of ammonia chillers. As the air gradually rises in the temperature, it also begins to rise physically and is collected in the larger return vents located at the top of the stands. Low-velocity jets and the top of the stands also shoot heated air into the expansive cavity above the pools, which help prevent any unwanted drafts in the comfort zone. Moreover, there was cavity space in the roof. If the cavity is not properly conditioned, condensation and the air quality would be serious problems. So the design team also made a ventilation system in the roof. They specified a series of large fans, which together keep the air into the roof cavity circulating until it can be collected and recycled. This air movement prevents condensation and problems with bad air quality. The heating and cooling system work closely with the ventilation and air movement strategies, dividing the building into major zones with different climate needs, including the pool deck zone for the athletes and the spectator zone. By dividing the stadium into zones, environmental needs can be met at the point of need, without influencing other spaces or trying to match the entire building and roof cavity to a constant temperature, which would require immense energy inputs. The heating and cooling system are, again, integrated with both water and ventilation systems, utilizing the oversized pool ducts for pipes and movements, while also using the properties and needs of water system to limit energy waste and increase efficiency. Detailing the facade, specifically at the curtain wall, was very carefully considered and detailed, both from structural standpoint and especially from a heating and cooling standpoint. The expensive curtain walls had to be self-supporting, and so a series enlarged vertical and horizontal mullions with attached steel trusses was implemented, which also allowed for the carefully considered radiant heating tubes to be installed within those same enlarged mullions. These same systems together allow for heating to occur directly at the point of largest heat loss, the curtain wall themselves. The heating tubes, which are filled with a water-based solution, are supplied from a mechanical filtration room, but the system, though accessible for repair, is completely self-contained, using pressure to move the water through the tubes, up and down the mullions, and across a few of larger transoms. The water heats up the air at the base of the curtain wall, which then rises until it reaches the top of the water, where it then begins to cool and descend softly back into the interior. This continued movement of air also helps to solve an even greater problem than comfort, that is condensation. The London Aquatic Centre organized the water system largely two main systems. One is double use of water and another is rainwater system. First is double use of water in the London Aquatic Centre. Abnormally, the overflow of water and the pool became water waste. But the London Aquatic Centre, the overflow of water at the pool doesn't turn into waste water. It flows to filtration room next to. The filtration room is located between the Olympics and practice pools and acts as the center of the building integrated function. The filtration room collects the backwash water, which is the used water at swimming pool or shower room, and they recover the used water by doing chemical usage and remove particles down to 1 micron. Finally, the room redistributes the water for the toilets in the locker rooms and public spaces that doesn't need clean water. This double use of all water is one of the greatest water moves of the building. As mentioned, the filtration room located at the center, it supplies the used water through the enlarged pipes to each space which need the water. And the London Aquatic Centre used other method for water system. The other method is rainwater system. Literally, when a rainy day, the massive gutter at the edges of the roof collects rainwater and makes to flow the water from top to the bottom following the wall slope. As the following effect, the rainwater flows along the roof and gathered in the massive gutter. And this rainwater falls into the bottom following the wall slope. The gathered rainwater can also be used to the facilities, toilets, and the showers, which account for the largest water demand in the facility. Through this double use of water and rainwater system, the London Aquatic Centre saves up to 32% water annually. Okay, this is the end of our presentation, and this week we have talked about interior construction, and we're going to talk about overall construction next week. And this is the role of team this week. Lee Jun-soo for the team leader and research, Ko Jae-sang for PPT, and Lee Myung-kyu for narration, Shin Sun-woong for research, and Yang Jae-young for research. Thank you for listening.